Our next section in Chapter 10.2 deals exclusively with sequences. The rest of the chapter will focus on series. The limits of a sequence. A fundamental question about sequences really concerns the behavior of the terms as we go further out and further in the sequence or at the end points of each graph from positive or negative infinity. Here you can see this formula, a sub n equals 1 over n squared plus 1, which is evaluated between n equals 0 and infinity. You can see that the terms stay positive, but they're getting smaller. And so eventually this will decrease closer and closer to 0. And we say that this sequence converges, and its limit is 0 as we go to infinity, as n goes to infinity. Here we have another formula, b sub n equals negative 1 to the n power times the quantity of n times n plus 1 over 2. And again, in this case, we're evaluated between n equals 1 and infinity. You can see that the terms increase in magnitude both in the positive and negative direction as we're getting larger and larger. And do not approach any unique value as the value of n increases. We do not have a horizontal asymptote. In this case, we say that the sequence diverges. Limits of sequence are really no different from limits at infinity of functions, except that the variable n assumes only integer values, not values between them like we normally saw with limits at infinity. And that leads us to the limits of sequences from limits of functions. Suppose f is a function that f of n equals a sub n for positive integers n. If the limit as x goes to infinity, f of x equals L, then the limit of the sequence a sub n is also L. Do note that L could also be positive or negative infinity. And we kind of have this situation where a limit is infinity, which of course by definition or idea of a limit is not really a limit. If a value goes to infinity, it's not constrained at all, which is what the definition of a limit sort of is. So you might also think of these as asymptotes, horizontal asymptotes. So as we're going to infinity or negative infinity, is the graph of the sequence, is it leveling out at some horizontal value as opposed to, increasing unbounded towards positive or negative infinity? So at the top of this slide, you can see a graph, and this really illustrates what we were talking about on the last slide, specifically that if a function or a sequence, levels out as we go to positive or negative infinity, it creates a horizontal asymptote at the value of L. In this case, L equals 1. So visually, you can see that there is a limit on this sequence. This sequence does converge to a number, a specific value, in this case L equals 1. And then you can see that the limit of f of x equals 1, which correlates to the limit of a sub n equals 1 as well as n goes to infinity. So here we're looking at the limit laws for sequences, and you'll see that these are correlate strongly or directly to limits at infinity for functions. Okay? Assume the limits a sub n and b sub m have limits a and b respectively, then number 1, the limit as n goes to infinity of a sub n plus b sub n, the sum equals the sum of those limits uppercase A plus uppercase B. If we do the same thing for number 1, this also works for differences. The limit as n goes to infinity of lowercase a sub n minus lowercase b sub n equals uppercase A minus uppercase B. This is just saying that we can take the limit of each term and then add or subtract those values to get the limit of a sum or a difference. Number 2 is the coefficient rule. The limit of a number times a sub n equals that number or coefficient times the actual limit of a sub n. If we take the limit of a product, again, this gives us, we can take the product of the limit. So if we're trying to take the limit of a sub n, b sub n, we can find the limits of each of those sequences, a sub n or b sub n, and then multiply them. This number 4 is the quotient rule, and this works the same way. The limit of a sub n over b sub n is equal to uppercase A over uppercase B, those limits of each sequence, of course, provided that b does not equal 0 because it's in the denominator. So these are things that you knew, learned earlier in math, specifically in Calculus 1 as we started studying limits as a bridge between algebra and calculus. This is nothing new, so it's just applying those limits at infinity for functions to sequences. So let's try our first set of problems, limits of sequences. So try these problems. These again are sort of like the function. So hit pause and try each of these 3 problems to determine the limits of these sequences. Okay, so if you think about the first one as a function, f of n equals a sub n, then f of x would equal 3x cubed over x cubed plus 1. If we divide the numerator and denominator by x cubed, we find that the limit as x goes to infinity of f of x equals 3. Because when you divide the numerator, you get left with 3 in the numerator. When you divide the denominator by x cubed, you get 1 plus 1 over x cubed. And as x is going to infinity, that term 1 over x cubed goes to 0. So we get 3 over 1, which is 3. You could have also applied L'Hopital's rule to this because you have infinity over infinity, and taking the derivative of each, the numerator and the denominator, I believe several times, and you would have got the same answer. So hopefully this kind of helps you kind of see how to solve these. And so if you didn't hit pause before, try it now and solve the last 2. For part B, we have the limit as n goes to infinity of n plus 5 over n to the power of n. If we rewrite this as 1 plus 5 over n to the n, this has the indeterminate form of 1 raised to the infinite power because the second term goes to 0. 5 over infinity is 0. So if we evaluate that, the limit of the natural log of 1 plus 5 over n to the power of n, this will equal, we can bring the power down in front, and we get the limit as n goes to infinity of n times the natural log of 1 plus 5 over n. Here we have if L exists, the limit as n goes to infinity of b sub n equals e to the power of L, okay? So what we've done here is take a log on both sides, and then in order to find the value of L, we have to raise it to undo the natural log, okay? Here we get L equals n to the power of n times the natural log of 1 plus 5 over n equals, now here all we're doing is moving this to the denominator, making it 1 over n, okay, which gives us the indeterminate form 0 over 0. So we can take L'Hopital's rule and take the derivative of the numerator and the derivative of the denominator. Once we do that, we can now simplify this to just 5 over 1 plus 5 over n, and of course the 5 over n goes to 0, leaving us with 5. Okay? Now we have to remember that the way we did this is that we took the log of the side, so in order to find the actual value of the limit, we have to again recognize that this is going to be e to the power of L, because this is what we found is the natural log of the limit, and so we have to undo that log, and so our actual limit value is not 5, but e to the power of 5, okay? Because we took the natural log of it and we have to undo it, as we saw. This is again from Calculus 1. All right, and our last problem here, C, the limit has the indeterminate form of infinity to 0. The limit as n goes to infinity is infinity over 1 over infinity, or infinity to the power of 0. So we first evaluate the limit of, as n goes to infinity, of the natural log of n to the 1 over n. Okay? This equals the natural log of n over n, right, by bringing the power down in front. And so we recognize, since we're taking the log, the actual limit is going to equal e to that power of L in this kind of interim step that we've created. Again, once we've used L'Hopital's rule, or the relative growth rates, we can find that L equals 0. And then, of course, the limit then equals e to that power of 0, which equals 1. So when we evaluate this limit, right, we get 0, and then of course we plug that on top of Euler's constant. There's some more exercises here in 14, 38, and 39. Try those, and remember that you do have access to the solutions manual through eCampus. There's a link there. So let's look at some terminology for sequences. We say a sequence is increasing if every a sub n plus 1 is greater than a sub n. It just means that each member is larger than the previous member. And you look at the graph here, you can see that this bottom sequence is increasing. The values are going up. We say a sequence is non-decreasing if a sub n plus 1 is greater than or equal to a sub n. So this is just takes the case when you have members that might be repeating, and you can see the sequence here, 1, 1, 2, 2, 3, 3. So it's greater than or equal to. Decreasing, each subsequent member, a sub n plus 1, is less than a sub n. So when we look at the set, we see that the members are going down. In the red, in the diagram to the right, the graph to the right, you can see this upper sequence is decreasing. And also we have the non-increasing in case members are repeated, but overall it's going down. So again, each subsequent member is less than or equal to the previous member. For example, 0, -1, -1. So here they're still going down, or they're staying constant to the previous member. We call it monotonic if it is either non-increasing or non-decreasing, and that just means it moves in one direction. And so both of these graphs are monotonic. The first one is the red one is non-increasing, and I believe that's blue or black. The bottom one is it's non-decreasing, okay? So it's also monotonic. We say a sub n is bounded above if there is a number m such that a sub n is less than or equal to m for all relevant values of n. And it's bounded below if there's a number n such that a sub n is greater than or equal to n for all relative values of n. If a sub n is bounded above and bounded below, then we say a sub n is a bounded sequence. Okay? So we can see in the graph here that both of these are bounded sequence. They have lower and upper limits. Because we're evaluating as n equals 1 to infinity, and we can see the upper, it's bounded above at y equals 2. It's bounded below The other one is bounded below at y equals 0. And then we're going to some kind of limit here, like the horizontal limit, which looks like it's at 1 for both of these, above or below. Okay, so hopefully the graph helps, and this language. Most of it's pretty intuitive. I think monotonic is a new one, and then these ideas of non-decreasing, which is increasing or equal. Non-decreasing is, hold on, I think I said that backwards. Non-decreasing is increasing or equal, and non-increasing is decreasing or equal. When you deal with negatives, this is why we avoid double negatives, because it's really freaking confusing. But even when you deal with negative terms like this, you really have to slow down, because it sometimes becomes counterintuitive for us. So let's look at our next example. Example 2, limits I'm sorry guys. Limits of sequences and graphing. Compare and contrast the behavior of a sub n and b sub n as n goes to infinity. Okay. Well, if we look at a sub n, if we divide the numerator and the denominator by n to the power of 3/2, we get 1 over 1 plus 1 over n to the 3/2 right here. And of course, as n goes to infinity, 1 over n to a power goes to 0, so we have 1 over 1, which equals 1. If we look at the graph, we can see that over here to the right. So this is the terms are positive, increasing, and bounded. Positive, all the terms are positive, they're all increasing, and they're bounded. It may look like they are non-decreasing, but each one goes a little bit closer to 1 without ever having reached it. Remember, this is going to 0, but it never actually gets to 0. It just gets smaller and smaller and smaller. And that's why it's increasing, not non-decreasing. Notice how slow I said that to try to make sure I did that right. Okay? Let's look at B, which is really the same formula, however, with a multiplier of -1 to the power of n. So what happens now if we look at the graph is that each of the alternate terms that we had in 1 goes to the opposite side. So when n equals 1, 1 to the, where am I at here? Sorry, 1 to the -1 to the 1 is -1, so the values start here. And then the second value, when n equals 2, is in positive. When n equals 3, it's negative. When n equals 4, it's positive, etc. Okay? So the terms of this bounded sequence alternate in sign. Using the results that we saw up here, the even terms form an increasing sequence that approaches 1, and the odd terms have a decreasing sequence that approaches -1. Therefore, because they don't go to one specific value, the sequence diverges. And this is really important. It can illustrate that simply the presence of -1 to the n power may significantly alter the performance or the behavior of a sequence. Geometric sequences have the property that each term is obtained by multiplying the previous term by a fixed constant called the ratio. They have the form of r to the power of n, or a times r to the power of n, where the ratio r and a cannot equal 0 and are real numbers. The value of r determines the behavior of the sequence. When a number less than 1 in magnitude is raised to increasing power, the resulting numbers decrease to 0. You think of this as a fraction. You know, when you multiply 1/2 times itself, or 1/2 squared, you get 1/4. 1/2 cubed is 1/8, and it's getting smaller and smaller. So these geometric sequences, for example, here we have 0.75 to the n. you can see that it converges down to 0. It gets closer and closer to 0, and in this case it would be monotonic because it's only going in one direction. If we choose r equals negative 0.75, we have the sequence negative 1 to the n, 0.75 to the n, okay? Observe that the factor negative 1 to the n, again, oscillates between the positive and negative, while 0.75n decreases to 0. Therefore, the sequence oscillates, but it still converges to 0. It's going on both sides of 0, but it's getting closer and closer. So it still converges to 0, even though it's coming from both directions. And when we have a number greater than 1 in magnitude raised to increasing powers, the resulting numbers increase in magnitude. And here we can see we have similar examples. Here we have 1.15 to the nth power, and you can see it's just increasing. And so this doesn't flatten out as we get to infinity, so we say this diverges, but it's also monotonic because it's only going in one direction. And finally, the last, here is where we have negative 1 to the n times the same thing, 1.15 to the n. And again, here we see it oscillating on both sides, the positive and the negative, but it doesn't converge to anything. It's still diverging. So it's oscillating and diverging here. So I think this is a great graphic from your text. This is Theorem 10.3 about geometric sequences, and it really kind of summarizes it, I think, in a really easy way to remember. So this is really a summary of what we just did in the last slide. So geometric sequences, r is any real number, and we have the limit as r goes to n to the power of n. And if r is less than 1, and if the absolute value of r is less than 1, so these are talking about values between 0 and 1, or fractional values less than 1, we saw that those go to 0 or they converge, okay? If r equals 1, then we just have 1 to the power of n, and 1 to any power is 1, so this will equal, I'm sorry, I went blank there, 1. So that's also in this middle area where it converges to 1, okay? If r is less than or equal to negative 1, or r is greater than 1, then we have divergence, and that's what you see on each of these sides, and these were those values of 1, absolute values of 1 that were raised to that power that we saw in the last slide. So anyway, I think this is a good graphic, especially I like the timeline at the bottom, or the number line at the bottom, and the convergence and divergence. I think this makes it a little bit easier to see what's going on. So let's look at example 3. Using limit laws, determine the limits of the following sequence. A sub n equals 5 times 0.6 to the power of n minus 1 over 3n, 3 to the power of n. And b sub n equals 2n squared plus n over 2 to the power of n times the quantity of 3n squared minus 4. Now remember, when we're looking to find out what these values are, we simply apply the limits as n goes to infinity. So hit pause and see if you can find both of these limits using the limit laws, which are, as we said earlier, or as I said earlier, I don't know who the we is, these are the same as limits at infinity for functions. So this first one we can see we have the limit of a difference, which means we can take the limit of each piece and subtract those. Also remember that if you have a coefficient in the front, you can apply that to the outside of the limit and find the limit of the function and then multiply it by that coefficient. So those are laws 1 and 2 from Theorem 10.2 earlier in this section. Okay? Well, here we can see that 0.6 to the power of n, this is a number less than 1. R is less than 1, so this converges to 0. We also see 1 over 3 to the n. What we've done here is rewrite the 1 over 3 to the n as 1/3 to the power of n, because remember, 1 to the power of n is still 1. So we can take that power and put it on the entire fraction, which we see here. This makes r, again, less than 1, which makes this converge to 0 as well. Since these both converge to 0, and 5 times 0 is 0 minus 0, we can see that this entire geometric sequence will converge to 0. Now let's look at B. And if you haven't done B yet, hit pause again. Try these on your own. You know, one of the dangers is just watching things. I don't know about you, but when I see things, I have this kind of maybe even psychotic way of thinking, oh, that looks really easy. I could do that. Even to the fact of like watching like Wimbledon or something in tennis, just watching something makes it look easy. And then when I go to try it, I'm like, wait, how did I do that? Or how did they do that? Etc. So I really encourage you that when I have this pause up here, that you stop the video, see if you can do the problems, look at the book, look at the notes from before, the notes you've taken, and see if you can work it through. Maybe don't look at the book because the book has the answer. That's where all these are coming from. All right, let's look at B. So here we have the limit of a ratio, but we also have this other factor in here. So if we take this factor of 2 to the power of n that's in the denominator out, then we have the limit of a product. So notice we can write 1 over 2 to the n, 1 over 2 to the n, as 1 over 2, 1/2 to the power of n, just like we did in the last example when we had 1 over 3 to the n. Because if we apply the, since the numerator is 1, 1 to any power is still going to stay 1, so it doesn't change that value. This then gives us the limit of a product, which we can then take the limit of each piece. In this first piece, we see that this is a geometric sequence with r being less than 1, r equals 1/2, so this is going to go to 0. Here we can apply our normal limit rules and divide each of the terms, the numerator and the denominator, by n squared. When we do that, we get 2 plus 1 over n. The 1 over n goes to 0. We get over 3 minus 4 over n squared, and the 4 over n squared goes to 0. So we are left with the limit equaling 2/3. So we finally have a limit of 0 times 2/3, which equals 0, of course. So even this limit converges to 0 because of the product factor, because of this factor of 2n. 2 to the power of n. So one of the most challenging ideas and concepts from Calculus 1 was the squeeze theorem. And the squeeze theorem for sequences works the same way. And the idea was trying to figure out what was happening as limits go to infinity for functions. And sometimes you couldn't quite tell because the function may be moving in different directions. And so the idea was, if you could find a function that was less than it on one side and another function that was greater than it on another side for all values of x, or in this case n, and if you could find that those were converging to some limit value, then by the squeeze theorem, because that function is always between those two values above and below, you could infer that or conclude that that function that you're looking at also goes to that limit value. The problem was, I think, in Calculus 1 and in most problems, is knowing when to use this first. So identifying, oh, this is a squeeze theorem problem. And then second, trying to figure out how do you find those functions that are always above and below it. And so we're going to look at an example here. You know, most of the problems in Calculus 1 had to do with trig functions, sine or cosine, etc. And even the example we're going to look at is a cosine function. Okay? So, where am I at? Okay, so again, the idea of the sequence, if there's three sequences, and B sub n is always between A sub n and C sub n, for some index, then, and if the limit of the lower sequence is equal to the limit of the upper sequence, and they equal some value of L, then because B sub n is always between them, it also must go to L. And the idea is, of course, that the upper and the lower sequences are actually squeezing them to that same value. So I know this is a challenge to figure out those problems, and if you can't find a value of the limit for your function, then maybe try the squeeze theorem. So guys, you've been at this a while. This is one of the longest lectures we've had so far, close to an hour. So this is a good time to take a break. Happy is the one who has acquired the love of walking for its own sake. W.J. Holland. What a great image, eh? So I recommend that you take a good 10 or 20 minute break. This is a long lecture. There's a lot of content here. Most of it's not overly difficult, but it's a long one. And so again, I recommend you take a break for at least 10 or 20 minutes and then come back and finish the lecture. So let's look at an example here. This is identified as the squeeze theorem. So see if you can figure out what would be the upper and lower limits, on each side of this b sub n, which is cosine n over n squared plus 1. So here's a good time to hit pause and try this. Okay. Well, we know that cosine of a value always goes between -1 and +1. So the lower limit would be the -1 over n squared plus 1, and the upper limit, or the upper sequence, would be 1 over n squared plus 1. So if we set up those three limits, and then if we can figure out what's happening with a sub n and c sub n, and see if they are indeed going to the same value, then we'll know that the limit for the b sub n sequence will be the same. Well, for a sub n, if we divide every term by n squared, we get 1 over n squared over 1 plus 1 over n squared, and as n goes to infinity, both of those go to 0, so we have 0 over n squared. Even though it's negative, it's still 0 over infinity is going to be 0. And by the same token, we would do the exact same thing to c sub n, and so we could see that both a sub n and c sub n are going to go to 0. Therefore, by the squeeze theorem, b sub n will also go to 0. And here you have a graph with the light blue is a sub n, the pink or red is c sub n, and then you can see barely in there the black, which is the cosine of n, or the formula we were looking at. Okay, so again, the hard part is recognizing these. Again, mostly I see these with, cosine and sine functions. And it gives you a couple examples there to look at, and those 65 and 67 are both sine functions, or trig functions, I should say. So next we're going to look at the theorem 10.5, that a bounded monotonic sequence always converges. And your textbook gives a great example of this using a cup of coffee. So I'm just going to read to you a little bit. Suppose you pour a cup of hot coffee and put it on your desk to cool. Every minute you measure the temperature of the coffee to create a sequence of temperature readings, T sub 1, T sub 2, etc. This sequence has two notable properties. First, the terms of the sequence are decreasing because the coffee is cooling on your desk. And second, the sequence is bounded below because the temperature of the coffee cannot go below the temperature of the room, of the surrounding room. In fact, if the measurements continue indefinitely, the sequence of temperatures converges to the temperature of the room. This example illustrates an important theorem that characterizes convergent sequence in terms of boundedness and monotonicity. Monotonicity, I like that word. So that's your extra homework assignment. Use monotonicity in a sentence in a conversation. All right. And here you can see these two cases of the theorem. In the first case, we see a non-decreasing sequence, all of whom terms are less than m. It must converge to a limit less than or equal to m. Similarly, a non-increasing sequence, all of whose terms are greater than n, must converge to a limit greater than or equal to n. So let's look at our next example, example 5, recurrence relations. Remember, that's when we figure out what's happening from the next sequence based upon the prior sequence. We have some kind of formula for the n+1 sequence as it relates to the prior sequence. Sequences for drug doses, example 5. Suppose your doctor prescribes a 100 milligram dose of an antibiotic to be taken every 10 hours. So we get a 100 milligram drug that we're taking twice a day, every 12 hours. Furthermore, the drug is known to have a half-life of 12 hours. That is, every 12 hours, half of the drug is eliminated. Okay? Find the sequence that gives the amount of drug in your blood immediately after each dose. B, use a graph to propose the limit of the sequence, that is, in the long run, how much drug do you have in your body. And C, find the limit of the sequence directly or analytically. So we know that after 12 hours, we have half of the dose that we just got in the prior dose, etc., right? Plus the dose that we're getting, so that's 100 milligrams here, okay? So try to solve this problem. See if you can first find the sequence, the recurrence relationship. That is, what is the dose dn+1 equal in terms of the prior dose? Okay? Pretty much just said it, actually. So if we set d sub n equals the amount of drug following the nth dose, and we know that the first dose is 100 milligrams, well, d sub 2 is going to equal 100, what was in our blood before, times 0.5, which is 50, plus our new dose for d sub 2, our second dose, which was 100 or 150. Okay, so we can see that each dose, d to the n+1, is half of the dose given before, plus 100, which is the amount given in this new dose. Okay, so a pretty simple relation there. If we graph this, we can see probably right after about 10 doses, and remember you get 2 doses a day, that's after about 5 days, the amount of the antibiotic in the blood is close to 200 milligrams steady. And importantly for your body, it never exceeds that 200 milligrams as well. Now, the explanation for finding the sequence directly is a bit involved and a little bit long, and so I'd like you to actually look in your text and to read through that solution. When I say it's long, it's long for me to describe, and I think the book does a good walkthrough of this example, and I'd like you just to look at that. It's only about a half a page, so it's probably 5, maybe 10 minutes of reading if you take your time and go through it. So to find the limit of the sequence directly, go ahead and look at the book, and I'm going to leave that one up to you. When we're talking about the growth rate of sequences, really what we're talking about is comparing multiple sequences and seeing which is growing faster. This is what we did with functions as well. Given two non-decreasing sequences of positive terms, a sub n and b sub n, which sequence grows faster as n goes to infinity? Now, the way we would do this, just like we would with functions, is we'd apply a limit as n goes to infinity of the ratio of the two functions. And we know if that ratio goes to 0, that means the denominator function or sequence is growing faster because we have a small number over a larger number, which goes to 0. If instead that as n goes to infinity, that ratio goes to infinity, then we know the numerator is growing faster because we have a larger number over a smaller number, which is growing and diverging. So that leads us to this theorem 10.6, the growth rate of sequences. And basically what this is an ordering. Okay, and so the most important part of this is this ordering at the bottom. And what these double less than signs means is that that this function to the right is growing faster than the one to the left. So this so the natural log raised to the power of q of n is growing slower than n to the power of p, which is growing slower than n to the power of p times the natural log to the power of r of n, which is growing slower than n to the power of p plus s, which is growing slower than b to the n, and b is greater than 1, which is growing slower than n factorial. Remember, that's like 6 factorial, 6 times 5 times 4, etc., which is growing slower than n to the power of n. And all of those exponents are any real positive numbers, and of course, again, b is greater than 1. Okay, that was the, I just went blank there, the ratio sequence that we saw before. Is that what it was? Ratio? Geometric sequence. I don't know. Ratio sequence. Sorry about that. Geometric sequences that we saw before with r greater than 1. Okay? What's important to note is that if you put a constant in front of any of these, and it doesn't matter the constant, it does not change the sequence. Okay? All right. So what we're going to do is we're going to use this sequence, knowing that, again, as we go to the right, these functions or sequences are growing faster, all right, to determine what's happening and compare growth rates. So let's look at example 6, convergence and growth rates. Compare the growth rates of the sequences to determine whether the following sequences converge. So again, what we're going to be doing is we're going to be using the formula, or from the theorem 10.6, we're going to be using the sequences of the sequences. That doesn't seem right. The comparative growth rates, this table, and that you see in green, remembering that the formulas to the right are growing faster than the ones to the left. And so we're going to be comparing the numerator and denominators, trying to figure out which of these formulas they relate to, and then decide whether they converge or not. Now remember, they converge if the denominator is growing faster than the numerator. They converge to 0. Okay, so hit pause and see if you can figure out these three, A, B, and C. Well, in A, we have the log of n to the 10th power, which is 10 times the natural log of n. So we have basically this first sequence, which is the smallest sequence, and then we have 0.0000 whatever 1 times n, which is just n, I guess, which would be this n to the p, where p would equal to 1. So we can see that the denominator is greater than, is growing faster than the numerator, and so this sequence converges to 0. Okay? Remember, it doesn't matter what any of these values are as far as the exponents, q, p, r, s, etc., which is kind of counterintuitive. And remember that last comment said that it doesn't matter the multipliers in front, which is also counterintuitive. You would think that 10 in the numerator being multiplied in the numerator would be a lot greater than 0.00001 in the denominator. But this is one of those places where our intuition kind of gets in the way. Okay? So try the same thing with B and see if you can figure out what we have. So notice the numerator is this function, n to the p natural log of n, where p would be 8 and r would be 1. And in the denominator, we have n to the power of 8.001, which is this function here, n to the power of p, where p would be 8001. So in this case, the numerator is growing faster than the denominator. And wait, did I do that backwards? Oh, look, I even made a mistake there. Gotta be careful. Now, why is this? What did I miss here? I was seeing this as n to the p, but we already used n to the p up here, n to the p natural log of r to n, and p was 8. So the denominator is n to the p plus s. We already defined p as 8, and so s would be 0.001. So this function is larger than that, so it does converge to 0. So be careful here. You got to look at all the options, and I made a great mistake there for you to learn from, just thinking of this as n to the p, but we had already done that here. So it's the same value of the exponent on n, but here it's a slightly larger. So hopefully that was a good mistake for you to hear as well as see, okay, and learn from. So let's do the sixth one. We have n factorial, which is here far to the right, and then we have 10 to the power of n, which would be representative of b to the n. So it looks like the numerator is greater than the denominator. Okay, so since again the numerator is greater than the denominator, then this should not converge but should diverge. Okay, let's see what happens. Again, we can see that this is going to infinity, and the sequence diverges. Here on the right we have a graph which shows a visual comparison of the rates. Because these sequences grow so quickly, we plot the logarithm of the terms, and the exponential sequence 10 to the n dominates the factorial sequence n factorial until n equals 25. At that point, the factorial sequence takes over, and it overtakes and becomes the larger and the faster growing sequence. As with limits of functions, there is also a formal definition of the limit of a sequence. The sequence a sub n converges to L provided the terms of a sub n can be made arbitrarily close to L by taking n sufficiently large. More precisely, a sub n has a unique limit L if given any lowercase epsilon greater than 0. It is possible to find a positive integer n depending only on lowercase epsilon, such that the absolute value of a sub n minus L is less than lowercase epsilon, or lowercase n is greater than uppercase n. If the limit of a sequence is L, we say the sequence converges to L, written the limit as n goes to infinity of a sub n equals L. A sequence that does not converge is said to diverge. The formal definition of a limit of a convergent sequence is interpreted in much the same way as the limit at infinity of a function. That lowercase epsilon that you're seeing that's here are really the tolerances, okay? Given a small tolerance, lowercase epsilon greater than 0, how far out in the sequence must you go so that all of the terms after that value of n stay within that range of the limit? And notice that it's on both sides. So when we're talking about tolerance, it's plus that lowercase epsilon or minus that. This is very typical in engineering as far as finding a tolerance or strengths when designing something. You know, if it's electrical engineering, you might be looking at power loads or something like that, and they have to be within certain tolerances or constraints. If you're building something physical like a bridge or a building, you have to have certain weight tolerances for you know, how much the building must support, etc. I don't know if this is one of those stories that they tell everywhere, but I remember when I was in undergraduate school at Syracuse University, the story was that when they built the new library, and it was like an 8-story library, the engineers and the architects forgot to include the weight of the books in the design of the library. And so the library's construction had to be delayed by about a year while they reinforced it to hold all of the weight of the books, and etc. Okay, this is a really challenging idea from Calculus 1, and students really struggle with this formal definition of tolerances, but it's really important. And so remember that this, with the convergences, we only have to deal with a tolerance on the y scale, on the limit, because we're talking about sequences that converge or diverge. Whereas before in Calculus 1, we often had to look at both tolerances as far as the output or the y value or the function value, as well as the tolerance on the input, etc. So this is a little bit simpler, but it's still a challenging idea. So let's look at the last problem in this section. It's been a long lecture, I know. Example 7, limits using the formal definition. Consider the claim that the limit as n goes to infinity of a sub n equals the limit as n goes to infinity of n over n minus 1 equals 1. Given lowercase epsilon equals 0.01, find a value of n that satisfies the condition of the limit definition. I think it's really important that you try to do this problem on your own without watching me go through it first. At least try it. This is one of the most challenging problems here, certainly in this section. Okay? What you want to remember is this tolerance formula from theorem 10. I'm sorry, not from theorem, but from the formal definition, that a sub n minus L has to be less than epsilon whenever n, lowercase n, is greater than uppercase n. If you remember this formula that's in green here, then you try to plug the values in and then solve for it. Notice what we're trying to do is find a value of n, okay, that satisfies this formula, okay? All right. See if you can do this. Now, again, what you're going to do is use this formula. Notice you have a value of epsilon here, 0.01, so I'm going to plug that in. We know our limit as n goes to infinity is equal to 1, so I'm going to plug that in for L. And we know that a sub n is this formula, n over n minus 1. So I'm going to plug that in here for a sub n. So basically, I'm substituting in other values for this whole tolerance formula so that I can then solve for n when it'll meet the conditions of this formula. Okay? Epsilon is 0.01. The limit equals L is 1. And a sub n is this formula, n over n minus 1. So when I plug that in, n over n minus 1 minus 1 equals, and this is just simplifying this by having a common denominator. I turn 1 into n minus 1 over n minus 1, so I get n minus n plus 1 all over n minus 1, or simply 1 over n minus 1. I'm not going to do this math about having a common denominator. That's certainly should be in your purview by now. And of course, this is less than the epsilon. Okay? Now all I have to do is solve this part of the equation. 1 over n minus 1 is less than 0.01. Well, I can remove the absolute value, so that makes it simpler because we know that n is greater than 1. Okay, we start at n equals 1 and go up, or n equals 0. Okay, so we're going to assume that the values for n are greater than 1 or at 1. Okay, that has to be greater than 1. What am I saying? All right. Now, if I invert, if I take reciprocals of both sides of an inequality, it changes the direction of the inequality. For example, if I have 1/2 is less than 3/4, and I invert that, 2 over 1, or 2, becomes greater than 4 over 3. So all I've done here is, so I get rid of the fraction on the left, I've take the reciprocal of both sides. So I get n minus 1 over 1, or just n minus 1, and 0.01 over 0.01, because this is 0.01 over 1. Okay? Well, this is equal to 100. When I add 1 to both sides, I get n is greater than 101. And that's really what I was trying to figure out, is the value of n that makes this true for everything. And so that value, all values greater than 101, will make this true. What does that mean? That a sub n minus 1 is less than 0.01 whenever n is greater than 101. And that's directly, notice how that falls directly from the tolerance formula in our formal definition. Okay? Try some of these problems. These are some of the most challenging.